We are missing a couple people for Kairos today, so I'm going to go ahead and record this. And we're going to start on this problem here today. So this is number 9. You'll notice this one also has bounds. And there's a couple reasons why we're going to notice that we might need U-substitution. Shirag, why do you think we might need U-substitution for a problem like this?
There's e raised to like a power.
Yep.
So that's chain rule.
Yep. And what else?
There's also product rule with the 3x.
Correct. There's also a product, right? We have a function times a function. So that's the key that tells us we're going to need some U-substitution. And so remember, when we choose our U, we want to choose a U whose derivative is available to us. Now, maybe the constant for that derivative is a little bit different, but we need to at least have the function, the x, raised to the correct power. Dennis, what do you think you might choose for your U?
X squared plus 4.
X squared plus 4. What would your next line of work be if you put U equals x squared plus 4?
Du, which would be 2x.
You're close. You have most of it. Remember, we're writing this in differential forms. Instead of writing it as du, there we go.
That's right. Yeah.
All good. So instead of writing it as du over dx, we're writing this in differential form, so it matches our form of our integral, and we get 2x dx. Now, I do not have a 2x dx in here, okay? I have a 3x dx, right? I've got this portion and this portion, but I do not have a 2x dx. Gus, what might you do next?
Would you put like a 3 halves outside of the du? That way when you like multiply the, like your 3 halves by 2, the 2's would cancel out and you'd get 3. Just left the one.
Absolutely. Perfect. So that works. So we want to end up with a 3x dx. So Gus is exactly right. What we can do is essentially divide by 2 and multiply by 3. So we get a 3 halves du, and then that will cancel out, and we're going to have a 3x dx. So Gus, while we're on you, why don't you go ahead and tell me how to substitute in this information into this integral now? And we'll do the bounds later. So we'll just leave these as is for now. How do I substitute all that information in?
So the first thing we want to do is make, so I'd say we'd have what, I'd put the 3 halves outside first. I can't forget our constant. So I'd put that there. And then I'd have a du times e to the power of u.
Okay, so this is close, but this is actually incorrect. And here's why. And we talked about this barely last time, but I'm actually glad you said this because it allows us to have a conversation. What this says is it says take the integral of like 1 and then take that and multiply it by EU, which is not what I want. The du has to come at the end of like the integral sentence. The du is sort of the brackets to say this thing says take the integral of, and then whatever is in between that and the du, that's what we're taking the integral of. So we can't actually write it in that order, but it's all the right information, Gus. So how would you write it instead?
So then I write instead e to the power of u times du.
Perfect. Exactly right. So that du and that little s sign, they have to be kind of surrounding the thing we're taking the integral of. Okay. Very, very good. All right. From here, we actually now have to take the integral. Now, if you guys remember, when I was taking derivatives, if I just asked you d over dx of e to the x, Conrad, what's the derivative of e to the x? Just e to the x. What's the derivative of that?
E to the x.
E to the x, right? Since it's just an x up there, it's just e to the x. So Conrad, by that same logic, what do you think the antiderivative of e to the u would be?
E to the u.
Perfect. Exactly right. So it's just an e to the u. Now we have a constant here. So that constant's going to come along, right? Oh, sorry, we haven't changed our bounds yet. But yes, that's right so far. We do have to actually go back and change our bounds. Sorry about that. Got a little ahead of myself. Ethan Balliser, how do we go about changing these bounds? So you'll notice on the bounds, I have a 1 and a 2 here. And those bounds, just like everything else in our original integral, are in terms of x. Everything is written in terms of x. So how do I get those bounds to be in terms of u, Ethan?
We just plug them back into the u is equal to x squared plus 4.
Perfect. And so for the bottom bound, what would you get for that bottom bound, Ethan?
5.
Perfect, because we're doing 1 squared plus 4, which is 5. And then what would you get for the top bound?
8.
So we get 2 squared, which is 4 plus 4, which is 8. Perfect. Okay. Now, the nice thing about when there's bounds on our integrals with U-substitution is we never need to come back to any of that X material ever again. We're done with it. We've used it as much as we're going to use it. Okay. And now we're going to actually go ahead and take the antiderivative, which we did. We got 3/2 e to the U. Remember, you're welcome to include the plus C. But since it's bounded, the C's are going to cancel out. So if you forget your plus C on a bounded integral, it's actually not a problem. It's okay. If it's unbounded, you have to have plus C. It's not wrong to include it. So if it's easier for you to remember just to include it every time, go for it. We're then evaluating this from our new bounds. So not from 1 to 2, but from 5 to 8. Nico, what would I get when I plug this in?
You would get 3/2 times e to the 8th plus c minus, in parentheses, 3/2 e to the 5th plus c, close parentheses.
Fantastic. What cancels out there?
The c.
Perfect. And what are you left with?
3/2 e to the 8th minus 3/2 e to the 5th.
Perfect, exactly right. And sometimes on an AP exam, they might factor out anything common. So they might end up factoring out the 3/2 and an e to the 5th and leave you with something like e cubed minus 1. As long as you're comfortable kind of rewriting this, maybe they just factor out the 3/2 and leave everything else in terms of e. That's it. That's your final answer though. Okay, are there any questions on this problem? What's our comfort level right now with U-substitution with bounds? Great, terrible, somewhere in the middle. Lots of greats, lots of in the middles too. That's okay. We're going to do some more practice problems. I don't see a whole lot of thumbs down, so that's great. Okay, let's go on to the next one. Okay, now we got some LNs, your guys' favorites. We did E. E wasn't that bad, right? And E, when you take the integral, is just e to the u, which is very nice, as long as you use that U-sub and get it down to just an e to the u. So go ahead and write this problem down. It's 1 to e, taking the integral from 1 to e. This one is ln x over x dx. Remember, you're choosing a u who you think's derivative is available. And the reason we would notice that we need U-sub on this one, Neil, why would you notice that we would need U-sub on this one?
Because there's a function of ln.
So a function of ln by itself doesn't like make us use chain rule, right?
Oh, because it's because quotient rule.
Because there's a quotient. Exactly, because there's a function divided by another function. So that would require quotient rule. When we're taking an integral, that's just U-sub. Okay, so ln x over x. I'm going to give you about 30 seconds to pick your u. See if you can pick your u. And I'll call on someone. And you're welcome to then write your next line of work. Might need to rewrite this a little bit. That's a hint. Without changing it, you might rewrite it a little bit. Let's go to Brian Luna. Brian, what'd you choose for your u?
ln x.
ln x. What would your next line of work be?
Du equals 1 over x du. Or sorry,
You're
dx.
very close. There we go. 1 over x dx. Perfect. Now what Brian noticed, and why I said you might need to rewrite this, is this is like 1 to the e of ln x times 1 over x dx. That's another way you can write the same information. So it might not be obvious that there's a 1 over x in this equation, but there definitely is. Okay, let's go to Noah. How would you now substitute that information in?
So you can you put equals and then u times du.
So that simplified quite a bit, right? We had this messy ln x over x thing, which is a disaster. Now we just have a u and a du. Noah, while we're on you, why don't you go ahead and help us change our bounds? So how do I go about
So
changing
you
those bounds?
plug in e to the u equals ln x, and then that would just be would it just be e?
Not quite. So ln of e, remember that question means log base e of e. And really what that means is e
one.
to, there
Sorry,
we go.
1.
So it means e to what power equals e. That's really what that question is. So you're exactly right, it's 1. So that goes on our top bound. Remember, whatever was on our top bound, if we sub it in, that goes on our top bound. Let's go to Anthony. How about our bottom bound? How would I find my bottom bound?
You're just going to plug in 1, u equals ln 1, and that's going to equal 0.
Perfect. And again, the reason for that is because that question really is saying e to what power equals 1, and so then that's 0. This integral has simplified quite a bit. Now it's just a basic u to the first power, right? We can use power rule. We just have a 0 and a 1. Go ahead and see if you can solve that and simplify it. And I'm going to call on someone shortly. Anthony, I think you might still be unmuted. Let's go to Mateo. Mateo, what'd you get from here?
So the next line would be u squared over 2 plus c, and then with 1 and 0.
That vertical line in 1 and
value.
0. Don't, make sure you don't draw an S or anything there. It should be a straight vertical line. Okay. And then from here?
And then you'd plug the 1 in. So you get 1 squared over 2 plus c minus parentheses 0 squared over 2 plus c. And the c's cancel out and you're left with just 1/2.
Perfect job. Exactly right. Mateo, harder question. In the context of the problem, what is 1/2? What is this thing that we just found?
It's the area under the curve from 1 to 0.
So you're close. So the first thing you said was right, area under the curve. Ethan Lee, can you help me out? What does this represent? 1/2. In the context of our original problem, what did we find? What's 1/2?
Did you call on me?
Yes.
Oh, sorry. I'm not sure.
Okay, do I have a volunteer? Does anyone think they know? Go ahead and unmute yourself.
The area under the graph from 1 to e.
Yeah, what graph?
Ln x over x.
Exactly right. So it's the area under whatever curve we have, like the area between that and the x-axis from 1 to e. So Mateo had said from 0 to 1. It happens to be the same area as the area under just a basic graph of u from 0 to 1. But what we were really finding in the context of the problem is the area under ln x over x from 1 to e. Okay, next one.
Quick question, Ms. Toshner.
Yes, go ahead, sir.
Just on that last question, can we go over really quickly again why when we change the bounds, we can just plug in 1 and 0 for u instead of having to plug in ln x for u?
Absolutely. So for this problem, since there are bounds, we changed everything so that now everything is in terms of u. So remember that this dx represented with respect to x. So we were finding with respect to x what that was equal. Using U-substitution, we changed the entire integral, including the bounds, to come up with an equal integral. So this integral is absolutely equal to the first integral. Okay, so what you could do, it would just be way more work. After you got to this step, Augie, after you got here, you could go back and plug this in for you, and then go back and plug in these bounds, because those are x's, and then evaluate. That would just be way more work because they're exactly equal to one another. So you could do that, you get the same answer. It's just a lot of extra steps that we don't need to do. Okay, because we changed our original integral with respect to x into something totally equal with respect to u, we can just use the simplified version since there's bounds. If there were no bounds, we know our final answer has to be a function, and that function should still be with respect to x, since our original function was with respect to x. Okay, does that answer that question? Awesome. All right, let's go on. So this next problem, go ahead and write this down. This one's a fun one. Gets a little tricky. This is going to use kind of several different examples we did over the last couple days. We have 1 over x times ln x. Again, you might think about how you could rewrite this. Okay, for this problem, we're going to go into our breakout rooms. I normally have you guys in breakout rooms. Let's see. Looks like most people still have at least a group of 3. Okay, so I was worried with Kairos that we were going to have different groups. So I'm going to just go ahead and open those rooms. I'm only going to give you, let's say, 3 minutes. I'll set a timer, work with your group. Make sure you unmute when you get there. Talk through this, talk through the different things, try something. Okay, and then I'll call you back. Go ahead now, should be open. All right, guys, welcome back. Hopefully we made some progress. This one was a bit tricky, which is why there's a nice, beautiful star next to it. Let's see how we did. Eli Reed, what did your group set up as your U?
We said the U was ln x.
Okay. And so what would your next line be, Eli?
The du is 1 over x dx.
Okay. So then what did you do from here?
If you plug those in, you get 1 over u du for the antiderivative.
Exactly right. So hopefully we got to this point. This is exactly right so far. Okay. It's helpful sometimes to rewrite that first integral. So just to explain, if that first integral is confusing the way it's written, you can write it as 1 over ln x times 1 over x dx. That's equal. Since there's no addition or subtraction, you can break up that fraction into just 1 over ln x and 1 over x. And so that sounds like exactly what Eli did. He got 1 over u, that's this portion. And then he said that this other part, 1 over x dx, was equal to du. Let's go to Ryan. Ryan, what'd you do from here? Oh, Ryan's on Kairos. Sorry. Matt Graff, what'd you do from here?
Then I integrated it and I got ln of the absolute value of u plus c.
Woohoo! And you did not forget the absolute value. Remember that absolute value, otherwise all of your work is wrong. Also, you need the plus c here because there's no bounds. So make sure you have the absolute value. Make sure you have the plus c. Fantastic job, Matt. Okay, we have one final step here since we don't have bounds. What do I need to do from here? Matt, are you on mute? Are you going?
Oh, I'm actually not sure what we need to do after this.
Okay, all good. Let's go to JJ. JJ, do you know what the final step here is?
Yes, so when I just substitute and put in ln of the absolute value of ln of x.
Yes, so now because we don't have bounds, we do actually need to go back to our u and sub back in whatever that was with respect to x. So that means, JJ, say that again, we're gonna get ln of what?
So ln of the absolute value of ln of x plus c.
Perfect, exactly right. Nice job. How many of you got that? Can I see a quick raise of hands? Wow, Noah sort of got it in his group. I like that. Sort of. Some of you guys were close. Yes, sir.
So do we only use the absolute value when we're going to have like a 0? So like if we take the integral of 1 over u and we would end up with u to the 0, is that when we use absolute value?
Yeah, so
then?
if you were, so I'm assuming where some of you got stuck is where we got stuck last class, where you tried to integrate this and then you end up getting u to the 0 over 0 and you get stuck. You're like not sure what to do with that. That's an indicator that we have ln. And since we are the ones introducing the ln to the problem, when we take that antiderivative, we need to include absolute value so it works. It's sort of like when we talked about like, if I have something that's x squared and I'm the one that introduces a square root, that's where we get a plus or a minus, right? If we're starting with a 1 over u and an antiderivative and we get the ln from that, then we have to include absolute value as part of that. Okay, but yes, it will happen anytime. If you were to try to use power rule and you end up getting u to the 0 over 0, that's a hint that it really should have been ln. Good question. Other questions? Okay, we're going to move on. We're going to talk about something you know and then something you don't know. So average rate of change and average value. These are the two averages you're going to see on the AP test. You're never going to see add them up and divide by 2, unfortunately. Sorry, we wish that was on here. But these are the two averages that we're going to see. So please go ahead and write this down. I would like put a star next to this page, or if you've got a highlighter or a colorful pen or something, make sure you mark this or note this. It's easy to mix these two up, okay? And so it's really important we understand the difference between them. So average rate of change we've talked about before. Aiden, Lynn, what's average rate of change?
It's like I don't know how to like, it's weird to describe. It's like it's basically how fast something is changing.
Okay, sort of. How fast something's changing at a moment would be an instantaneous rate of change.
Oh, how
right?
fast it's changing over a period of time.
That's true. Okay, does anyone think they have another explanation or an equation or anything that would represent average rate of change? Noah, go ahead.
Was it the slope of a secant line?
That's one thing, right? It's the slope of a secant. So what Aiden was saying was like, it's the rate of change between 2 points, maybe. So he said over an interval, I would say specifically between 2 points. So if like a point here and a point here, and we find the, starts with an S, anyone know what word I'm going to say? If we found the, what of that line? That would be the average rate of change.
Slope.
Slope, right? We're finding the slope of that line. That's the average rate of change. Okay, that's the slope of the secant line. And so that's what we're finding when we're finding average rate of change. What's the equation, Ben Budnick, that we would use to find average rate of change? What would the equation be?
Yeah, f of b minus f of a over b minus a.
Perfect, exactly right. And you guys remember, that's just regular slope. That's like y2 minus y1 over x2 minus x1. But that's the actual equation we've used before. Like if I give you a function f of x and I say find the average rate of change between 0 and 4, you plug in 0, you plug in 4, and you plug it into this equation, right? That's average rate of change. Average value is going to find something different. Instead of finding the slope between 2 points, it's going to find the most expected output value. That's what average value is going to find. It's going to find the most expected output value. Or like, what's the average y value we would get over an interval? So not the average slope, but the average y value. Our equation is very different for average value. It's, copy this down, 1 over b minus a. The integral from a to b of f of x dx, where f is the thing we're trying to find the average value of. Okay, so we set it up as 1 over b minus a, the integral from a to b of f of x dx. Okay, does everyone have that written down? This might seem like malarkey for now. We're going to do some practice problems with both to make sure we understand. Okay, so basic problem, this should be review. Find the average rate of change of f of x equals x squared on 1 to 4. Let's go to Nathan Wise. Nathan, what would I do to solve for this? How would I find this average rate of change?
He's on Kairos.
Ah, thank you. George, what would I do to find average rate of change?
To find average rate of change, you will do f of 4 minus f of 1 all over 4 minus 1.
Perfect. So I need a couple pieces for that. So we need to find f of 4. So how would you find f of 4?
So you could plug in f of 4, so you'd have 4 squared into the equation we're given, and we would get 16.
Perfect.
And
then
we
what?
can do the same thing for 1. We can do f of 1, which is 1 squared, which equals 1. So we'll have 16 minus 1 all over 4 minus 1.
Okay, keep going.
Which equals 15 over 3, which equals 5.
Perfect. Okay, George, what does that 5 represent in the context of this problem?
The average rate of change, or the average slope of the secant line from between those points on that, on the interval 1 to 4.
Perfect. So I've got x squared, right? That's like a parabola, something like this. So we said, okay, between this point and this point, we'll call that 1 and 4. We found that we have a slope of 5. That's what we found. We didn't take any derivatives, but by the way, on this one, right? All we did was regular slope. Okay. Questions on this problem? This should be review. We've done that. You guys did this in pre-calc, right? This is totally review. Average value is different. So I'm going to choose the exact same function and the exact same interval, but we're going to find a very different thing. So average value of f of x equals x squared on 1 to 4. Again, the basic equation here is 1 over b minus a from a to b of f of x dx. I would write that down. Even though you just wrote it down, I'd write it down again, just to make sure that you have it. The more you write it down and practice that basic equation, just like f of b minus f of a over b minus a, the more comfortable you're going to be utilizing it. Okay, I'm going to walk through this one for you. Try to get a little bit like one step ahead of me. Like right now I'm talking a lot. Maybe see if you can write down some of the stuff that you think is going to go in here, and then I'm going to help you out. Okay, so this is essentially our A. This is our B, just like we did on the last one when we found f of b minus f of a. We used f of 4 and f of 1. So that means on the outside here, I'm going to have 1 over my b, 4, minus my a, 1. Then I'm going to take an integral. And on that integral, it's going to go from 1 to 4 of f of x, which in this case is x squared, dx. That's our setup for average value. Now we can simplify this a little bit. That 1 over 4 minus 1, that's just the same as 1/3. So we have a constant out in front. We know that for that constant out in front, we're just going to apply that later. Now I chose sort of an easy antiderivative. We don't have any U-sub on this one, right? We can just use power rule to evaluate this. And we're taking that integral from 1 to 4. Let's go to Naman. Naman, what is the antiderivative of x squared?
I got 1/3 x to the 3rd.
You got 1/3 x to the 3rd. So I'm going to call that x cubed over 3 for just the antiderivative of the x squared part. What else do I need to include, Naman? Oh, you're a little hard to hear. I'm going to come back to you. Sorry about that. Charlie, what else do I need to include along with that x cubed over 3?
The constant 1/3.
Yeah, so we have this constant out in front. Sorry if you said that, Naman. I just can't hear you very well right now. So we have that constant out in front. We need to include that as well. So we're going to get a 1/3 times our x cubed over 3. Charlie, what would you do next?
Well, you can simplify that to x cubed over 9.
Okay, so we have an x cubed over 9. Okay, what else do I need to include here?
Oh, your bounds.
Yeah, so we're actually evaluating this from something to something. So again, you could include the plus c if you want. You don't have to because there's bounds. Those c's are going to cancel out. Okay, but either way, so if you want to include it, it's never wrong to include. It is wrong to miss it if there were no bounds. Okay, so yes, Charlie, you said we're going to include our bounds. We're going to go from 1 to 4. Let's go to Augie. When we evaluate this, what do I do next?
You're going to start by plugging in 4 for x. So you're going to have 4 cubed over 9 plus c that whole quantity minus 1 cubed over 9 plus c.
Okay, keep going.
And then the c's are going to cancel out, and you're going to get 64 ninths minus 1 ninth, which is going to end up being 63 ninths, or 21 thirds, or 7.
We just really got to take our time to get there. Love it, Avi. Nice job. Okay, excellent job. So we got 7. So we got a totally different answer, right? Similar function, same interval. This was asking for average value versus average rate of change. So again, the average rate of change found the slope between those 2 points. What we're finding now is the most expected y value. So what we're saying on x squared from 1 to 4, like we're trying to figure out what the most average output value is. And so the most average output value on that interval is 7. That's the most expected output that we're going to get. Okay, questions on that problem? All right, let's do another one. This says find the average value of f of x equals sine x on 0 to pi. F of x equals sine x on 0 to pi. Remember, the equation for average value is different than the equation for average rate of change. So it's important we read this correctly. Average value is 1 over b minus a, the integral from a to b of f of x dx. I'm going to send you guys back to your breakout rooms really quick. Let's see how far you can get. I'm going to give you probably about 2-3 minutes again. Let me go ahead and open those up.
Hey, I tried to jump into the room and then it pulled me out of there.
I moved you to room 1 so that you would be in a different room. I'm impressed. Lots of you back early this time. We feeling more comfortable with our trig stuff, hopefully? A little bit? Getting there? Unit circle stuff? Waiting on 2 more groups, it looks like. Okay, so I think everybody is back now. From the first groups that were back, they said they felt pretty good about it. Is that how we're feeling in general? 2 thumbs up from Charlie. Love it. Awesome. Okay, so let's go to Dennis. Dennis, what did you do from here? So we just have our basic setup. What'd you do from here?
Okay, I just plugged in values. So I got 1 over pi times the interval of 0
So I'm
to
going to put pi minus 0, just so everyone knows where those values came from, Dennis, but you're right. It is just 1 over pi. But just so everyone can see the b and the a, I'm just going to write both to make that clear. Okay, and then go ahead.
Interval of 0 to pi sine x dx.
Fantastic job. Okay, from here, what would you do?
I took I took the interval, so it's 1 over pi times negative cosine x.
Perfect. And so again, remember, it's the opposite of whatever the derivative is. So the derivative of sine is cosine. So the antiderivative of sine is negative cosine. Or you can make that little ladder that I always show. So sine, cosine, negative cosine, and back to sine. If we're going down, we're taking a derivative. If we're going up, we're taking an antiderivative. Since we were at sine, we would go up and we would end up at negative cosine, just like Dennis said. So we have negative cosine x. Keep going from there, Dennis. What else did you have on this line?
So that's it. Or sorry, the big line.
Good.
So yeah, 0 to pi.
Okay, excellent job. From here, let's go to Justice. Justice, what'd you do from here? Mr. Navarra, are you with us?
I don't think he is.
Okay, we'll figure it out later. Noah, what'd you do from here? Looks like we just lost a couple guys. Noah, what'd you do?
So then from here, I plugged in the bounds into negative cosine x. So I actually, yeah, so 1 over pi times negative cosine pi minus, and then parentheses, negative cosine 0. And then negative cosine pi is 1, negative cosine 0 is negative 1. So it'd be 1 minus negative 1 is 2. And then multiply that together, 2 over pi.
Bravo! Fantastic. Okay, excellent job. Common mistake is students will forget about this thing out in front, or that 1 over b minus a part. That's a pretty common result. So if you just got 2 as a final answer, you forgot to incorporate this 1 over pi that we have all along the way. So you should end up with a 2 over pi. Okay. Or other common mistake, students just start plugging in pi and 0 into sine. They just actually forget to take the antiderivative altogether. They're doing all this other mental work. And so they just start plugging in it. Make sure you actually take the antiderivative. So if you ended up getting an answer like 0, that also means you plugged it into the wrong thing. Are there any questions on this problem? Awesome. Okay, we're going to do one more thing. This is kind of a weird question. I've seen this kind of a question on a lot of AP exams, actually. And so I don't need you to write all this down. I just want you to think through this together. This is where it gets a little confusing. And so feel free to ask questions. We have about 5 minutes left, and this is the only thing we have left to do. Okay, so it tells us we're given 3 functions. We're given acceleration called a of t. We're given velocity called v of t. And we're given position called x of t. So those 3 functions, we're not told that like a of t equals t squared plus whatever. It's just called a of t, v of t, and x of t, okay? And what I want to do is write 2 ways to find the average velocity. So using those different functions, I want to write 2 ways to find the average velocity on 2 to 7, okay? Now, average velocity, please write this down, can be represented by 2 ideas. It can either be the average value of the velocity, that's equal to an average velocity. An average value of velocity is an average velocity, okay? They just don't put the word value in there, but that's what that would be. An average of something really is like secretly average value of that something. Okay, so average velocity means the average value of the velocity. Does anyone know another kind of average, hint we only have 2, that could also find the average velocity?
The average slope of acceleration.
So you're close. I wouldn't say average slope. I would say the other words that we have. So average rate of change. But it's not of acceleration.
Of position?
Of position, right? So average value of velocity gives me average velocity, but so does the average rate of change of position. Because average rate of change of position means we're finding the slope of the position graph. And the slope of the position graph means I'm going to end up with something like feet over seconds. Right? If I have an x of something minus an x of something else, that's like maybe feet, and then divided by a time, that's going to give me a feet over second. So let me show you how to set this up. 2 ways we can find our average velocity, our average value of the velocity, which means we're using this interval from 2 to 7. So 1 over 7 minus 2. Oops, that just looks like 72. From 2 to 7 of the velocity of v of t dt. This would be that first way. That would be the average value of the velocity, which would find the average velocity. The other thing we could do is x of 7 minus x of 2 over 7, minus 2. That would be average rate of change of position. Now I want to prove to you that these are equal. Okay. So if we go back and look to the left at our average value of the velocity, If I took an integral of velocity, what function would I end up with? So we know if we take a derivative of position, we get velocity. If we take a derivative of velocity, we get an acceleration. What I'm saying is, if I take an antiderivative of velocity, what function do I end up with?
Position.
Position, exactly right. So if I take the antiderivative of v of t, what I end up with is still this 1/7 minus 2. And we end up with x of t, that's our position function, from 2 to 7. Right? The antiderivative of velocity is position. If I were to plug in the 7 and the 2, I would get 1/7 minus 2 times x of 7 minus x of 2. Well, that's exactly equal to this. Those two things are exactly equal to one another. So sometimes you're given velocity and asked to find average velocity. Sometimes you're given position and asked to find average velocity. So you would just use the method that has the correct functions available to you. Okay, the same thing would work with average acceleration, except you would use average value of acceleration and average rate of change of velocity. Good. This was kind of a heady topic. Are there any questions on this one? Okay, guys, so that's all I have for you today. I'll stay on the call if anybody has any questions. Remember, tomorrow you have the entire period to work on Quest. I will be checking. You will be assigned Jug if you do not work effectively for the duration of the period. Hopefully you're feeling okay with U-Sub. Hopefully you're feeling okay with average value. We do have a quiz on Monday. So make sure you're ready. Reach out with any questions to your classmates, to me, or to Google Classroom. Okay, I'll stay on if anybody has any questions. Otherwise, have a great day.
Thank you.
Thanks, y'all.
Thank you, Ms. Toffner.
Thank you. Question,
Ms.
Augie?
Toffner, yes.
Yeah.
So tomorrow, I have a baseball game during.
Fun.
So how do I get a signature or like